Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. We're going to take a short break from derivatives and revisit our limits. We've seen these two limits on the screen here before, and we've shown that it's true by looking at the graph of the function. But that's not exactly a proof, is it? So why is it that it's true? Today, we're going to take a look at this idea at a deeper level and make use of some of the old trig techniques and limit techniques that we've explored in the previous playlists. Be sure to brush up on some of those old skills through the linked videos below before proceeding with this one if you need to. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. So what we're going to do here is we're going to prove this limit first. And once we've proven this one, we're going to use this limit to prove the second limit. Now, to prove the first limit, we are going to start by drawing a diagram. We're going to draw a circle where the origin is at 0, 0, but we only need the part that exists in quadrant 1. So let's say this circle has a radius of r. Next, we're going to go ahead and draw a terminal arm, and we're going to call our angle theta. So here, this is our theta. And then we're going to drop a vertical line down to the x-axis. So this is a right angle triangle. So let's go ahead and label our diagram here. The origin, that is going to be called O. This intersection point here, let's go ahead and call that A. This point up here, we're going to call that B. And then this point down here, we're going to call that C. So there are three shapes that we're interested in here. We have our triangle OBC, and then we have another triangle, which is OAC. So let's go ahead and write that down, triangle OAC. And the third one is not a triangle, but a sector of a circle. So from O to A to C. So we're going to call that sector OAC. And notice that OA here is also a radius, so let's go ahead and label that as R. Now, because we're trying to prove the limit as theta approaches 0, it is okay for us to limit our theta to be greater than 0 and less than pi over 2. So meaning here in quadrant 1. So we're going to let theta be between 0 and pi over 2. Then what's going to happen is from this diagram, we can clearly see that triangle OAC has the smallest area, and then sector OAC is going to be a little bit bigger because it has this extra area right over here. And then triangle OBC is going to have the greatest area. So that means we can go ahead and write down the relationship between these three. So we would have triangle OAC is less than or equal to the sector OAC, which is less than the triangle OBC. And here we are talking about the areas. So now the area of triangle OAC, we can use the formula 1/2 of AB sine theta, where A and B are the two sides of the triangle, and theta is the angle in between A and B. So here we can see that our A and B would be R, and then the angle in between is theta. So therefore, the area of triangle OAC is 1/2 times R squared times sine theta. Now the area of sector OAC is 1/2 times R squared times theta. And you can find that by using the area of a circle multiplied by the proportion of the sector to the whole circle. And then finally, for triangle OBC, we can see that our base here is R, but we need to go ahead and find the height, which is BC. Now let's go ahead and draw a smaller diagram here. So our triangle OBC has an angle theta right here, and then the base is R, which tells us that tan theta is going to be equal to the segment BC over R. So therefore, the height here is equal to R times tan theta. So this is our BC. And the area of that triangle is going to be half of the base times the height. So that is going to be 1/2 times R squared times tan theta. And now we can go ahead and simplify this a little bit. So since r squared is always positive, we can go ahead and divide everything through by 1/2 r squared. And the inequalities are not going to change directions. So then we get sine theta is less than or equal to theta, which is less than or equal to tan theta. Now if we go ahead and divide through by sine theta, this is going to give us 1 is less than or equal to theta over sine theta, which is less than or equal to. Now recall that tan theta is sine theta over cos theta. So that means dividing it by sine theta is going to give us 1 over cosine theta. And notice here the inequalities did not change direction because sine theta is positive in our defined domain. And now this is slowly starting to look like what we want to prove. The only thing now is that we want sine theta over theta instead of theta over sine theta. So let's go ahead and flip the fraction for all three of these expressions. So now remember that if we flip our fractions, our inequalities are going to flip. So that means we get 1 is greater than or equal to sine theta over theta, which is greater than or equal to cos theta. And now we're going to go ahead and apply our limit. So since right now our domain is greater than 0 and less than pi over 2, the limit is going to be theta approaching 0 from the positive side. And we're going to do that for all three of these expressions. We're going to take the limit as theta approaches 0 from the right-hand side. And then once we do that, we can see that our first expression, well, that's just going to be 1. And then cosine of 0 is also going to be 1. So now the limit that we're interested in is sandwiched in between 1 and 1. So by the squeeze theorem, we can say that the limit as theta approaches 0 from the positive side of sine theta over theta is equal to 1. So again, this is by the squeeze theorem. So now we have proven that the right-hand limit is equal to 1. So we're going to repeat the same process for limit as theta approaches 0 from the negative side. And it's going to be very similar. The only difference is that you have to watch out for the sign, because when theta is in between 0 and negative pi over 2, that means we're in quadrant 4, which means sine theta is going to be negative. But we're actually going to take a shortcut here, and we're going to use the fact that sine theta over theta is an even function. So meaning we're going to let the function f of x be equal to sine x over x. Then f of negative x is going to be sine of negative x over negative x. But sine of negative x is just negative sine x, and that's because sine is an odd function. So that means this is equal to negative sine x over negative x. So now we can cancel out the negative sign, and this is equal to sine x over x, which is just equal to f of x. So when you have f of negative x equaling to f of x, this is what we call an even function. And because it's an even function, we know that if we take the limit as theta approaches 0 from the left-hand side of our function, so sine theta over theta, that is also going to be equal to 1. So now since both the left side limit and the right side limit are equal to 1, we can now finally say that the limit as theta approaches 0 of sine theta over theta is equal to 1. All right, now that was somewhat of a long one, but now the hard work has been done. So the second limit is going to be much easier for us to prove. So the second limit, we have limit as theta approaches 0 of cos theta minus 1 over theta. So what we're going to do is we're going to multiply both the top and the bottom by cos theta plus 1. So we get cos theta plus 1 over cos theta plus 1. So expanding the top, we get limit as theta approaches 0 of, and this is now going to be cos squared theta minus 1. And then the bottom, we're not going to expand. We're just going to leave it as theta times cos theta plus 1. Using the Pythagorean identity of sine squared theta plus cos squared theta is equal to 1, we can replace our numerator with negative sine squared theta. So then we get limit as theta approaches 0 of negative sine squared theta over theta times cos theta plus 1. And now we can go ahead and split this up into two limits. So the first one is limit as theta goes to 0 of sine theta over theta. And then we're going to multiply that by limit as theta goes to 0 of negative sine theta over cos theta plus 1. So now the first one, that's the limit that we just proved. So this is equal to 1. And then as for the second one, we can go ahead and substitute that in because we're no longer dividing by 0. So by doing a direct substitution, we get the top is 0, and then the bottom is equal to 2. So we get 0 over 2, which is 0. So now we have 1 times 0, so therefore this is equal to 0. Okay, so now we're going to take a look at a couple more examples where we can put them to use. The first one is to find the limit as x approaches 0 of sine 5x over 3x. So in order to use our limit, we need this argument to be the same as the denominator, right? Because it has to be sine theta over theta. So then that gives us a hint on how we want to start this. So we want the limit as x approaches 0 of sine 5x, and we want the bottom to also be 5x. But that's not what we currently have. Currently, our denominator is 3x. So what can we multiply this by in order for the denominator to become 3x? Well, if we multiply this by a 5 on the top, that 5 is going to cancel out with this 5 on the bottom. And then in order to get this 3, we just need to go ahead and make our denominator here 3. So now, convince yourself that this is the same as that, because once we cancel out the 5, the denominator is going to be 3x. And now we can go ahead and pull the 5 over 3 out in front of the limit. So then this is 5 over 3 times the limit as x approaches 0 of sine 5x over 5x. And we know that this is equal to 1. So therefore, this limit is equal to 5 over 3. Now for our second limit, we're going to go ahead and use our double angle identity. So we get limit as theta approaches 0, and sine 2 theta is equal to 2 sine theta cos theta. And the denominator here is cos theta minus 1. Next, we're going to multiply the top and the bottom both by the conjugate of the denominator. So that will be cos theta plus 1 over cos theta plus 1. And once we do that, we get this is the limit as theta approaches 0. So now the bottom is cos squared theta minus 1, which we can use the Pythagorean identity and change that to negative sine squared theta. And then our numerator stays the same, which is 2 sine theta cos theta multiplied by cos theta plus 1. And now one of the sine thetas can cancel out. That means we're left with the limit as theta approaches 0 of 2 cos theta times cos theta plus 1 over negative sine theta. So now it seems like we're kind of stuck because there isn't any more algebraic manipulations that we can do. But notice how as theta approaches 0, our denominator here is going to approach 0, but our numerator is not approaching 0 because cos theta is approaching 1, which means cos theta plus 1 is approaching 2. So our numerator here, it is approaching 4. So we have a number that's close to 4 divided by a number that is close to 0, which means this is now going to be infinity. So therefore, the limit here does not exist. And now let's do a quick recap of what we covered in this video. We proved these two trig limits through past trig and limits knowledge. And we're actually going to revisit these two limits again in a future video where we will show another method to prove them. That is going to be much simpler. Then we looked at a couple more examples where we had to use algebraic manipulation to create these two limit patterns in order for us to evaluate trig limits. And now it is your turn to give this a try. Can you evaluate the limit on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.